bar and like stretch it out before the hook. It sounds like a pirate, and you know you can have hooks. But then if you are the end, it's a hooker. So.
Oh my god.
Anyways.
This is on the recording again.
It is on the recording again. All right, stop picking on him. He's a good boy.
Really?
Yeah. All right, elasticity and spring energy. I want to talk about the idea of a graph for elasticity and spring energy. And so if I talk about the horizontal axis being a delta x axis, the amount that you've stretched a spring by, and I talk about the vertical axis being the applied force, or I guess the responding force by the spring force, I could say that as I stretch this spring, and we talked on the blackboard about the fact that the units would be newtons per meter for a k constant. As I stretch this spring, what you notice is that as I stretch it, the amount of force that the spring responds with increases. It increases linearly because of this whole equation that we came up with before, Fs equals k delta x. It increases in magnitude linearly. And as it increases in magnitude linearly, what you notice is that that means the slope is constant. So the rise over run would be force over delta x. Force over delta x being slope, also force over delta x, according to this equation, is k. So what does the slope of this type of a graph represent? K, bingo. All right. Slope is k. Yeah. Yeah, units all work out. And now here's the other neat thing about this graph. You know how in kinematics we spent some time finding the areas underneath of graphs? Yeah. Let's find the area underneath of this graph. If I wanted to find the area underneath of this graph, I would talk about the maximum force and I would talk about the minimum force. But if I had a maximum force and a minimum force, do you think I could talk about like an average force? Yeah, why not? So we could talk about there being like, all right, Fs max, I guess, plus Fs minimum, 1, 2, divided by 2 would be some average force. You could do that. Is there another way that I could deal with finding the area under this thing? Yeah?
Just do the area of the triangle.
Base times height divided by 2? Okay, let's try that. The base is delta x.
And then times the max force divided by 2.
Sure.
Use delta V. Is delta X not delta V?
Oh, sorry, delta x. Messy. Delta x times F max divided by 2. That's going to be equal to the area. Now this delta x here is also the delta x max, just so you recognize that. So I want to recognize that F max, off to the side, F max is equal to k times delta x at the maximum position. So I'm going to sub that into this position here. And I say that delta x is equal to, delta x times k delta x over 2 is equal to the area. Or I could simplify that and I could say, all right, well that's kind of the same as saying k delta x squared over 2 is equal to the area. Or I could say that a slightly different way. I could say 1/2 k delta x squared is equal to the area. Does that look familiar to anybody in terms of the blackboard work that we've done previously?
Yes.
What's the area represent? Energy. Yeah, if I can find the area under a graph such as this, it's the spring energy within that spring. Okay? So just like in kinematics there was a reason to find the slope, Now there's a reason to find the slope for this graph. It's the k value. And just like in kinematics we had a reason for finding the area underneath of graphs, there's a reason for this one. It's to find the energy. What if you do a lab someday, you can imagine, and you get an f versus delta x graph that looks something like this, where it doesn't end up being perfectly linear because you don't end up getting an ideal spring. But what if you got a graph that looked something like this? Without using calculus, is there a way to approximate the area underneath of that graph, do you figure?
Yes.
Must be, otherwise I wouldn't ask. What if I broke it up into bars? What if I said, okay, look, there's a bar, there's a bar, there's a bar. I made the bars of equal width. There's a bar. Pretend I got it just perfectly equal. Okay. I could turn this curvilinear graph into a bar graph, and this is a great approximation method for finding the area under a curved graph. And the area under this graph would be the energy stored in the spring at the maximum stretch length. What I could do is I could carve it up. And I'm going to carve it up very intentionally. The way I'm going to carve it up is so that the midpoint of each horizontal line in my bar graph intersects with the curve. And there's a reason for that. The reason is that if I use that approximation method, really what you'll notice is that approximately at least, this triangle here and this triangle here are the same area. So the area that I'm adding extra into my bar graph is approximately equal to the area that I'm neglecting on my bar graph that would be under the curve. Can you see that? It's sort of an approximation geometry thing. And it's not perfect. Much like a line of best fit, if you do it by hand, isn't perfect. This isn't perfect, but it's a nice approximation method that lets us avoid having to come up with a function of best fit, our curve of best fit function, and use calculus. We can sidestep calculus here, and we can do a little approximation method. Let's just get that in there. You know, I know in the next couple of years you're going to have the calculus under your belt anyway, but it's nice to be able to do this sort of thing and be able to talk about the ideas without having the higher level math. Okay? And we could do that for each bar graph. We'd just be talking about finding the width of that particular bar and the height of that particular bar, and of course doing that for each bar, adding up the areas, and it would get you right back to finding the energy. Yep?
But if you, for like calculus, like to the side, if you found it at each point, would you just be fs?
Yeah. So in calculus, if you found the area, well, you guys haven't talked about integration yet.
The derivatives of energy is k times delta x.
Yeah.
So then you wouldn't at any point.
Well,
Whatever that energy
I'm not sure that you guys have gotten to integration or antiderivatives yet, but that's where it's going. It's finding the area under graphs, and even curvilinear graphs if you know the function of that graph.
Okay.
So this is the baby steps, and this is a great baby step. This is something that people did maybe for a long, long time. It's actually a nice way if you're an ancient farmer and you live in a country like China, yes. If you're an ancient farmer and you live in a place that has lots of curvilinear landforms and you want to tax the people, you can break up those landforms into strips, and you can do the exact same thing only with your geography. So if you ever find yourself in a time machine in ancient China, where there's lots of rivers, by the way,
I feel like that's definitely bad.
it's entirely probable that you will be in this situation one day. You can figure out how much acreage you have by this bar graph method and a simple map. And you can maybe argue with the authorities about how much taxes you owe based on the area of your land. And I guess you'll see where you get with that. But you can prove it to them. Look, this is the acreage I have. Okay, so it's not just for graphs. It's actually a nice thing for calculating biomorphic shape areas if you don't happen to know the formula.